Hi guys, welcome to the lecture on variability and z-scores. So let me start with a story. By the mid-1980s, the American space program had lost its sparkle, so to speak. So shuttle flights had become routine, so routine that the major networks stopped broadcasting them live, and NASA really needed something to reignite public interest. So in 1984, President Reagan announced the Teacher in Space project. So the idea was that NASA would select an ordinary classroom teacher, not a scientist, not a military pilot, a teacher, and send them into orbit on the space shuttle. The idea was brilliant. The idea was brand new. There was no idea of space tourism back then. Not everyone knows an astronaut, but everyone knows a teacher. Every kid in America could see themselves in that teacher. So over 11,000 teachers applied, and NASA chose Krista McAuliffe. She was a 36-year-old social studies elementary school teacher from New Hampshire. She was the mother of two. She was warm. She was funny. She was instantly likable. When a journalist asked about the mission, she said, "If you're offered a seat on a rocket ship, don't ask what seat, just get on." She appeared on Good Morning America, The Today Show, The Tonight Show with Johnny Carson. She became one of the most recognized faces in America overnight. Her motto was, "I touch the future, I teach." So she was very relatable. Everybody loved her. She planned to broadcast 2 science lessons from orbit and have them live beamed directly into the classrooms across the country. And schools prepared for this for weeks. And teachers built lesson plans around the launch. Bulletin boards went up. NASA set up a special satellite feed so schools could watch. This was going to be the day that space belonged to everyone. On the morning of January 28, 1986, millions of school children sat on classroom floors, including me, by the way. I was only 5 years old, but I remember this. We sat on classroom floors, and they wheeled in these big television sets. There were no flat screens back then, so there's just these big, massive TV sets that they would wheel in on carts. And so everybody, millions of kids around the country were watching, and McAuliffe's husband and her own 2 young children and her parents were watching from the viewing stands at Cape Canaveral.
SRB hydraulic power units have started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Now control. Roger, roll, Challenger. Good roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
7 crew members were killed. Commander Dick Scobie, pilot Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, and of course Krista McAuliffe. In the investigation that followed this, it really became clear that engineers had tried to stop the launch the night before. They had data from 23 previous shuttle flights. They were worried about the cold temperature, 36 degrees Fahrenheit that morning, far colder than any previous launch, and they recommended delaying. NASA managers pushed back. They asked the engineers to prove it was unsafe. The engineers had the numbers right in front of them, but they couldn't organize them. They couldn't present them in a way that would make the danger undeniable. So management reversed the engineers' recommendation, and unfortunately, the launch was approved. I'm not going to tell you exactly what went wrong, not yet. Instead, I'm going to give you the same data the engineers had, 23 launch temperatures from 23 different spaceship launches. And I'm going to teach you every tool in today's lecture by computing it on those 23 numbers. And by the end, you will see what they couldn't communicate. You'll be able to quantify precisely how dangerous that launch was in a way that probably would have worked for the management. So your job is to figure out what went wrong, what killed these 7 people, and why no one could say it clearly enough to stop it. Here are the 23 launch temperatures sorted for you from coldest to warmest. So 53 ranging up to 81. And the proposed Challenger launch temperature was 36. So everything we learned today, we're going to learn on these numbers. Okay, so let's talk about the mean first. For the mean, hopefully you guys remember what the steps are. Try pausing it right now and doing it yourself. If you don't remember, you're going to add up all of the values and then divide by the sum of values. So if you didn't remember that, now pause and do it. So add up all of these temperatures, 53 plus 57 plus 58 plus 63, on and on and on. That's going to equal 1600, and then divide by a total of 23 temperatures. 1600 divided by 23 is 69.57. Okay. Oh, I guess I should be writing this out for you. Okay, so the mean is the total of the values, right, divided by the total number of values. So you add all them up, you get 1600 divided by 23 total, and that's going to equal 69.57. 9.57 degrees. That's the average. So basically 70 degrees. The average launch temperature across all previous shuttle flights was about 70 degrees. The median is another way to measure central tendency. It's the middle value, right, when the data is sorted from lowest to highest, which I've already done for you. So to find it with 23 data points, well, pause it and try it yourself if you can remember the formula. If you can't remember the formula, let me give it to you. So make sure you pause it if you don't want the hint. So the median is, it's always n plus 1, but I like to think of it as it's from 1 all the way to how many values there are. So 1 plus n, right? And n, for this case, would be 23. Okay, so 1 plus 23, and then you're finding the halfway point, so you divide it by 2. So 24 divided by 2 equals 12. Now, is the median 12? No, the position of the median is 12. Okay, so this formula is telling you the position. So we've got position 12. And then you count to the 12th position in the list, and that value is 70. Okay, so this tells us something important. Half of all launches happened, maybe lunches too, but launches happened at the temperatures below 70, and half happened at temperatures above 70. 70 is the halfway point. So the median gives us a different perspective than the mean, which is that it's not affected by extreme values the same way. Okay. Now the mode, okay, is the most common number. Okay, so that should be pretty easy. So if you look at our data, let me go back to those numbers. Okay, if you look at what the most common number is, what has the highest frequency, it's 70. Okay, so the mode is also 70. So the mean is about 70, but is being pulled down by that extreme outlier of, what was it, 36 degrees, I think. And then the median is 70, the mode is 70. So the distribution is obviously very symmetrical, right? It's not bimodal because all three of these are the same. And so all three give you a good answer of what is the typical launch temperature. But does it answer our question of, is it safe to launch at 36 degrees? Okay. Does the average of 70 degrees, 70 mean, 70 median, 70 mode, does any of that help you answer that question of, is it safe? And the answer is no. Okay? None of them tell you anything about whether 36 degrees is dangerous. They don't tell you, and you might say, well, 36 is way different than 70 degrees. That's a lot colder. And that's the point of this lecture, okay? The mean itself doesn't tell you anything, but the variation between the mean and this new value is what tells you something, okay? The mean, the median, and the mode don't tell you how spread out the temperatures were. They don't tell you how far 36 degrees is from, the pack. They don't tell you whether anyone has ever launched in conditions even remotely this cold. So central tendency tells you where the center is, but the center is not the question here. The question is, how extreme is 36 degrees compared to the center, compared to everything that came before? So to answer that, you need to know about how spread out the data are. That's what we call variability. Variability is how spread out are the data. So you just experienced firsthand the limitation of central tendency. The mean tells you the center, but the center says nothing about spread, how far the individual values range from that center, and whether any particular value is normal or, crazily different, extraordinary. So variability measures the spread, okay, versus the center. And this matters for three reasons. Reason number one is you can often have the same mean, the same average, but totally different reality of the data set. So two data sets can have exactly the same mean, but tell completely different stories. So imagine, for instance, in two classes, you have both classes have a 75% exam average. Class A, those scores from 72 to 78. Everybody's performing about the same. But in Class B, the scores range from 50 to 95. So some students are failing, others are acing it, but both have the same average, but completely different situation in both classes. So in Class A, the mean is a good guide. It's a reliable guide. Everyone is close to 75. In Class B, the mean describes almost nobody. It's a mathematical fiction. Okay, so our launch temperatures have a mean of basically 70, but if you only knew the mean, you wouldn't know whether launches cluster tightly around 70 with low variability, or whether they range from 53 to 81, which is higher variability. The mean alone can't tell you. If the only number you had to make this decision was the mean is 69.6 degrees, and today it is 36 degrees, that would tell you nothing about whether it was safe or not. Reason number two of why we like to look at variability is variability determines statistical conclusions. So here's the technical point that will matter for the rest of this course. Most statistical tests ask one question: is the effect big relative to the amount of noise? So think about, like, if you're talking to somebody. If you're in a quiet room, it's very easy to hear what they're saying. But the louder and louder, the more noise there is, the harder it is to pick up what that person is saying. It becomes much more difficult to understand them because of all the noise. And that's what we talk about in statistics. You have the noise versus the signal. The signal is the person talking to you. The more noise there is, the more variability in the data, the harder it is to hear what the data is trying to say to you. Okay? And variability is this noise. So the noise is variability, the effect that you're looking at to see, is my research good? Did I get an effect? Is this significant? That's the signal. Okay, that's the data speaking to you, trying to tell its story to you. So nearly every test in statistics is structured as the effect divided by the variability. Okay, you've got effect, the data speaking to you, divided by the noise in the room, the variability. Okay, the more noise, the more the effect is divided up so that you can't hear it. The less strong the effect is, because it's being divided by all the noise. So high variability, if this denominator is very high, the higher it is, the smaller this fraction is going to be, and the harder it is to find significance. Okay, low variability. So if the denominator is low, then that makes the fraction large, which mathematically we're saying that it's easier to find significance. But you can think of it as, this is the signal, the data speaking to you is being divided by the noise, and the more noise there is, the less you can hear the signal. Okay, so reason 3 is that variability itself is important. So oftentimes in research we think of variability as this irritation. It's taking away from our ability to hear the effect. But sometimes variability itself is the signal. Sometimes variability is what we need to be looking at, and many times is more interesting than the signal itself. And in the Challenger disaster, variability was the story. Variability was what we needed to hear and to look at. With the Challenger data, the mean was totally unremarkable. 70 degrees, it's a pleasant temperature, it's nice, okay? But that's all it is. It was the spread of temperatures. It was all that variability and what happened at the cold extreme that contained the life or death information. So the average told you nothing, the variability told you everything. Okay, so let's measure it. We'll start simple and we're going to build towards more powerful tools. So the simplest way to measure how spread out data are is the range. Okay, so the range is simply you find the highest value, you find the lowest value, and you compute the distance between. So range equals the highest max value, and then you subtract the minimum value, and then you get the range. Piece of cake. Okay, so for our 23 launches, okay, so these are the numbers. So the maximum number is 81. That was the highest value. The lowest value was 53. Okay, easy. And so that's how you calculate the range. You're going to take that the max and then minus the minimum. Okay, and 81 minus 53 is 28. So the range is 28 degrees. Okay, previous launches span 28 degrees, excluding this new launch, right? So now look at that. The proposed Challenger launch, that's 36 degrees. So that tells us that it's outside of the range, right? That's 17 degrees below the minimum. Okay, 17 degrees below the coldest launch in the entire history. So that fact alone should have raised alarms, but the range does have serious limitations. First of all, even though it's 17 degrees below, is that huge? I mean, the average was 70, right? And at 53, they're launching at almost 20 degrees below what the average was, and it went fine. That spaceship didn't blow up. Is another 17 degrees that significant? So the range doesn't really tell us the significance. It doesn't tell us if that 17 degrees difference really is big or not. It kind of feels big, but it probably feels bigger because you know what happened. The managers didn't know, they obviously didn't know that it was going to blow up. So for them, 17 degrees didn't seem like a big deal, okay? And the range has some other serious limitations too. So it uses only 2 of the 23 values, the most extreme ones, and it throws away everything else in between. So it's extremely sensitive to outliers. One unusual value can change it dramatically. So if we looked at, 36 degrees, so 36 to 81 would be the range, right? And so you're going to have a much bigger range in this case, and this is a huge outlier compared to all of the rest of the temperatures. Maybe in that list they had one at 37 degrees. They managed to do a successful liftoff at 37. So you've got a range of 37 to 81, and then you have a spaceship launch at 36. And the managers are like, what's the big deal? It was 37 before. Okay, but 37 is weird compared to the rest of the temperatures. So maybe you managed to survive that one, but are you going to survive the next one? How unusual it is. How dangerous was it to launch at 37 degrees? Okay, so the problem is sometimes the outliers give us useful information. Sometimes the outliers distort the picture. It just sort of depends on what you're looking at. But the range is very sensitive to outliers, and it just doesn't give you a lot of information. Okay, so the ranges can be helpful if you just want kind of a quick glimpse, but otherwise it's not super powerful. Okay, so the range does give us something useful in this case. 36 degrees was far below anything that was previously tested, but it can't tell us how unusual that is relative to the overall pattern. And for that, we need to look at the middle of the distribution, not just the endpoints. Okay, so this is when we look at the interquartile range, or the IQR, okay, because it's just way too much effort for us psychologists and mathematicians to say interquartile range. Inter means between, that's Latin, okay, and quartile means a quarter of it, 25% of it, okay, so interquartile range. So the range looked at the extremes. Now let's look at where most of the data lives, okay? Specifically, we're going to find the boundaries of the middle 50% of launch temperatures. This is what the interquartile range does. Why the middle 50%? Because it ignores the most extreme values on both ends, where the outliers are, where the noise is, and focuses on the central bulk. And that gives us a measure of spread that's stable, that's robust to being pulled to either side with the outliers. Okay, so remember in this example, the outliers are useful, but in much other research, the outliers screw things up. Okay, outliers are more likely to sort of screw up what you're trying to get to at the research than to actually help. So let's say you have a class of students that are scoring, you know, from most of them are getting Fs on an assignment, but you have one student come in who gets an A. The range would be all the way from F to A, and it's like, well, the students are all over the place. But it's just that one student that got an A. Everybody else is failing. So it makes it look like overall you're doing pretty good with teaching the class. But it's just the one student that did good. And so they're distorting the picture by being an outlier, being an extreme. So sometimes it's useful to just cut out the extremes. Okay, let's just cut out the extremes and let's look at what most people do, what the central 50%, the vast majority of people. Remember the bell curve where most people are in that center part, like 70% or whatever, are in that middle part. So the range looks at the extremes, the two extreme ends of the values, but the interquartile range looks at the mid 50% so that those outliers are ignored. Okay. So we need to find the three key values that divide the data into 4 equal parts. Okay, so the interquartile range. So if you divide this into 4, you've got 1, 2, 3 parts, right? And then quarter 1, quarter 2, quarter 3, quarter 4. So you need to find these 3 points in order to find in order to divide the data into 4 parts, all right? So these 4 parts are all quartiles. Quartile 1, quartile 2, quartile 3, quartile 4, okay? So first, we're gonna find this middle point here, okay? That middle point. So that middle point is easy. You already know how to do this because the middle point is called the median, okay? Very easy. So easy to find, and we've already done the math for this, right? So it's 1 all the way to how many values there are, 1 plus n. So 1 plus 23 is 24, and then you have it in order to find the middle. So 24 divided by 2 is 12, okay? So the median is the position 12 of the 23 values, which we know is basically 70, okay? So 70, change color again, 70 is that middle value, okay? In quartile language, that is quartile 2, the second quartile, okay? So next, let's find the middle of the lower half, okay? So you're going to take all the values below the median, so everything below the median, positions 1 through 11, okay? So 53 all the way up to 70, and actually, you know, I think I did this wrong. I think this is the median one. But anyhow, it's 53 all the way up to 70, right? So there's 11 values. So you're just going to do, basically, you're finding the median of the lower half, okay? So that's 11 values, so 1 all the way to 11, 1 plus n is 1 plus 11 is 12, divided by 2 is 6. So the 6th position, which is... Oops. 1, 2, 3, 4, 5, 6. Okay, so now 67 is the first quartile, quartile 1. Okay, so the first quartile marks the 25th percentile, which means that 25% of all launches were colder than 67. Okay. 50% of all launches are colder, okay, colder than 70. That's what this is saying. The percentile means everything is below this. If you're in the 25th percentile, 25% is below you. 50th percentile, 50% of everything is below you. Okay. And then to find the middle of the upper half, you're just going to do the same thing. You're just going to do the median formula. So now it's the same exact thing, right? So you take all the values above the median, so positions 13, okay, 13 through 23, okay, 70, 70, 72, 73, 75, blah, 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 all the way up to 81, okay. And then we already did the math for the first half of the median, right, and we got 6. So 1 to n, so 1 to, how many were there? 11, okay. So that's 12 divided by 2 is 6, so obviously still the 6th position. So let's see, 1, 2, 3, 4, 5, 6. Okay, so now 75. So position 6 of this group, 75, that's quartile 3, the third quartile, okay. 70, let me do the other color, 75, okay. Now the third quartile, we've got 25%, we have 50%. It shouldn't surprise you that this is now 75%, okay? So that means 75% of all launches are below this temperature. 75% of launches are colder than a temperature of 75 degrees. So if we write this out, okay, quartile 1 is 67, quartile 2 is 70, quartile 3 is 75, okay, 75 degrees. And now you know what it means to be at quartile 1, quartile 2, or quartile 3. Okay, and then obviously at the very top, you're going to have the highest value, which is 81, and 100% of values, you know, are below 81. That should be clear because obviously everything in your values listed out is lower than 81. So that should be pretty obvious. Okay, so this sort of just tells you how extreme things are, how unusual it is. If you're in quartile 1, that's pretty unusual. If you're in quartile 2, still unusual, but less so. Quartile 3, yeah, not so unusual. Quartile 4, well, everybody, you know, is somewhere in quartile 4, or below quartile 4, I should say, right? So, okay, so hopefully that makes sense. So that's the interquartile range. Now, or at least the basic understanding for it. Now let's calculate, okay, the 50%, the middle 50%. That's what we want to know. So the distance from quartile 1, so quartile 1 to quartile 3, actually let me write that better. Quartile 1, this is how we write it, to quartile 3, is the width of the middle 50%. So that equals the middle 50%, okay, middle 50%, which is what we call the interquartile range. Goodness, I can't write today. So again, if we look at that, okay, we've got quartile 1, quartile 2, quartile 3, and then quartile 4 is over here at the end that we just don't mark that down. The middle 50% is quartile 1 to quartile 3. You see that? It's very simple. I know the vocabulary and terminology is weird, but it's a simple concept. We're just looking at the middle 50%. And now we're going to calculate it. Again, very easy, but to calculate the interquartile range, okay, you're just going to take quartile 3, because that's the biggest number, subtract quartile 1 from it, and then that equals the interquartile range. So we know from this page, right, that quartile 3 was, circled the wrong one. Quartile 3 was 75, okay, so quartile 3 is 75, and quartile 1 was 67. Okay, easy. And so the interquartile range is 8 degrees. Okay, the vast majority of launches were within 8-degree range. Okay, really simple. 67 to 75 is almost every launch. The majority of launches, dropping the extremes, was in that range, an 8-degree range. So the middle half of all launch temperatures spans just 8 degrees, which is a very narrow band. Most launches, again, happen between 67 to 75, which is not surprising because it's normal, comfortable Florida weather. So if you've seen a box plot, like in a research article or whatever, then the IQR is the interquartile range. I'm sorry, the IQR is the box, okay? So this box, okay, that I just drew, is the interquartile range. So this would be, 67 at this end to 75 at this end, and then you've got, the extreme ends of the range. So what was that? I think it was 53 to 81, was it? Let's double check. Yeah, 53 to 81. So this is just giving you the entire range, okay? The range was 53 to 81, and then quartile 1 and quartile 3 was 67 to 75. So if we eliminate the extreme outliers, then we get this box, which is poorly drawn, but which is the interquartile range. Okay, hopefully that's making sense for you guys. And again, the advantage of that is that it's eliminating the outliers so you can see what's normal. So the interquartile tells us what's normal, but the nice thing is if we know what's normal, we can also say what's abnormal, okay? So this is when we start looking at outlier fences. What now is, if we know what's normal, what is an outlier? So we're going to use the interquartile range or the IQR method to identify the outliers, what's outside the fence of what's normal. So normal things are allowed in the fence, abnormal things, they're kept out. So we call them the upper and lower fence, okay? So we're going to identify what's outside of the fence, the values that are unusually far from the rest of the data. So first, remember what IQR is, okay? The interquartile range measures the spread of the middle 50% of the data. And we calculate it. Let me just write this down for you. Okay, to get the interquartile range, we do quartile 3. Just ignore that, okay. Quartile 3 minus quartile 1. Okay, I guess I could do an equal sign there. Equals the interquartile range. Okay, so now statisticians don't just eyeball outliers, right? We create the fences, the statistical boundaries that tell us when a data point is far enough away to be considered unusual. So the formula for this is, we have a lower fence and we have an upper fence. If you think of it as a field, right? Or the box. What's on the outside at the low end of the field, what's on the outside at the high end of the field or the upper end of the field. So a lower fence and an upper fence. So for the lower fence, the way we calculate that is quartile 1 minus 1.5 times the interquartile range. Okay, and that's going to equal the lower fence. Now, why 1.5? Number 1.5 isn't arbitrary. It comes from research showing that for most reasonably symmetric data sets, okay, normally distributed, values more than 1.5 IQRs away from the middle 50% are rare, okay, but not impossibly rare. So in other words, less than 1.5 IQRs is normal variation, and more than 1.5 interquartile range is unusually extreme, okay, and worth investigating. So this cutoff balances two goals. So we don't want to flag normal values as outliers, but we do want to catch values that meaningfully deviate from what's typical. Okay, so that's why 1.5 is the standard used in box plots and exploratory data analysis and so on to figure out what the lower and upper fence is. Okay, so again, just to say that one more time, what we discovered with looking at research is that if things are more than 1.5 interquartile ranges away from the middle, 50%, then they're very rare. Okay, so in our data, remember what we calculated? Let's see, where did we do that at? So we calculated the interquartile range was 8 degrees. 8 degrees is the 50% range in that data set. So if it's more than 1.5 times 8 degrees, then it's unusually high. If it's less than 1.5 times 8 degrees, it's unusually low. Okay? So to find the lower outlier fence, again, you're going to take quartile 1 minus 1.5 times the IQR. So if we plug that in, let's look back at our data. So quartile 1 right here, okay, was 67 degrees. So we've got 67 minus 1.5 times 8. Okay, 1.5 times 8 is, let's see, source 12. So 67 minus 12 equals 55 degrees. So if it's lower than 55 degrees, it's unusual. That's what we're saying. If it's lower than 55 degrees, it's unusual. And we do the same thing on the high end, okay, the upper fence. So we start at quartile 3 because that's the edge of the interquartile range. So quartile 3 minus 1.5 times the interquartile range, okay, equals the upper fence. So we know that the interquartile range is 8, right? So times 1.5. And quarter 3, okay, you just go back to your research. We already figured out what quartile 3 is. It's 75. Okay, so 75 minus 1.5 times 8, which is 12. 75 minus 12 equals, plus, because, sorry. So quartile 3 plus 1.5 times interquartile range, because we're trying to figure out what's unusually high at the upper fence. So we're going to add instead of subtract. Sorry, so hopefully that's not confusing. So the upper fence is quartile 3, so the top end of the interquartile range, plus another 1.5 times the interquartile range. So another 12 degrees above is normal, but more than 12 degrees is abnormal. So 75 plus 12 is 87 degrees. Okay, so the lower fence is 55 degrees. Anything below that is unusual. The upper fence is 87 degrees. Anything above that is unusual. And anything in between is considered okay. Maybe it's outside the interquartile range, but it's not so far out that we would say, oh, well, that's crazy high or crazy low. So here's the critical insight, right? The coldest previous launch occurred at 53 degrees. That temperature falls below the lower fence of 55, meaning it was already flagged by the data as an outlier. They should have been worrying about that launch at 53 degrees. That's already an outlier. Okay, maybe it's only 2 degrees, but still that should be concerning if it's an outlier. Okay, and and if you look, this is kind of getting into the correlation statistics, but we won't talk about that. So if you look at the performance data for the spaceship, one of the things that they looked at that's very important is something called O-rings. O-rings are just these little rubber gaskets that, because they're kind of fluffy, they seal things and they keep things from leaking. And that same launch, the 53-degree launch, had the worst O-ring performance data in the entire program's history. So already at 53 degrees, we saw some parts of the spaceship failing. And that's only 2 degrees below the lower fence of the interquartile range. So this is not a coincidence. The interquartile method doesn't know anything about rockets, doesn't know anything about O-rings or engineering failures. It's simply identifying temperatures that are outside of normal operating conditions. So the fact that the worst failure occurs exactly at an outlier temperature tells us something really powerful, that cold temperatures are statistically associated with increased O-ring failure risk. So the math was warning us clearly before the disaster ever occurred. So if someone had done this calculation the night before, which takes 2 minutes with a pencil, and said, by standard statistical criteria, this temperature is a severe outlier, even our coldest previous launch was flagged as unusual, and it had the worst performance we've ever seen, this launch is 19 degrees beyond even that, that's a statement that stops a room, okay? Or at least it should have. So, but the IQR ignores half your data, right? The top 25% and the bottom 25%. For the statistical test you'll learn later on, we need an even more powerful tool than the interquartile range. And these tools will also show you even more easily how dangerous this launch was, okay? And so we need a measure that uses all the data, and that's where variance comes in, okay? So We want to know on average how far each value is from the mean. That seems like a natural way to measure spread. Compute each value's distance from the center and average those distance. So let's try it and see what happens. So for each temperature, we're going to subtract the mean from the value to get the deviation. So you have your value and you're going to subtract the mean. Okay, so value minus the mean. Okay, and hopefully you guys remember that that's the Greek symbol for mean, mu. Okay, so that's going to tell us, this difference is going to tell us the deviation. And deviation is simple. It's just how far is the value from the mean. That's all it means. How far are you deviating? How far from normal are you? And normal is the mean. How far is that value from the center and in which direction? Okay, so take 53 degrees, right? So again, x minus mu, or the mean. So x would be 53 degrees minus the mean, which is 69.57. Okay, so if you calculate that out, you have negative 16.57. So that's 16.5 degrees below the mean. That's how much it deviates from the average, from the normal. Try doing this with 70. Okay, so again, x is your value, and pause and do this yourself. See if you can do it. So x is 70 minus the mean, which again is 69.57. So what does that calculate out to? Feel free to use your calculators. That is, in this case, a positive, not negative, 0.43. Okay, so basically at the mean. It varies a little bit, but not much. 70 degrees is the value. 69.57 is the mean. So barely deviates from normal. 81 degrees, which I believe was the highest temperature, right? So 81 minus 69.57 equals positive 11.43. So that's 11.43 degrees above the mean. Okay, so you're seeing how far values deviate from the mean. Okay, makes sense, easy. Now here's a problem. If you add up all the values, okay, so all of the temperature values, not just these three, but all of the values, all 23 deviations, these are all the deviations. If you add them all up, you get exactly 0. Always, every time. This isn't a coincidence, it's mathematics, okay? The mean is the balance point of the distribution. So the positive deviations, the values above the mean, always perfectly cancel out the negative deviations, the values below, okay? So the sum is always 0. So if you have something that's equally balanced, it's going to have the same amount of weight on either side. The deviations are the weight. So whatever positive deviations you have up here, you'll have matching negative ones, at least matching when you add them all up. They always add up to 0. So let me give you an example. Okay, we'll just do something really simple. You have a deviation of plus 1 and minus 1. Okay, it's going to equal out to 0. Okay, now obviously you're going to have a lot more distribution. Let me put up a photo of that. So these are the deviations of the 23 data set. If you add them all up, they equal 0. Okay, which is a great trick to know, because if you want to double check that you calculated the deviations right, just check that they all sum to 0. Okay, so this means that we can't look at the average of the deviations, because if you add them all up, you get 0. So 0 divided by 23 is still 0. Messes up the calculation. The answer will always be 0, regardless of whether the data is tightly clustered or wildly spread out, high variability or low variability. And 0 tells us nothing about the spread. Okay, so the trick is just to get rid of the negative signs. Okay, easy, piece of cake. So what we do is we simply take each deviation and we square it, because a negative times a negative equals a positive. Okay, easy. So if you take plus 1 squared and negative 1 squared, that would equal 1, positive 1, and also positive 1. In our temperature data, a deviation of negative 16.57, negative 16.57 times negative 16.57 becomes positive 274.57. And a deviation of positive 11.43 squared becomes 130.60. Okay, no more canceling. When you add them all up, then they no longer cancel each other out. Okay, so if you add up the squared deviations, this gives you a single number, which we call the sum of squares. So in our simple example, 1 plus 1, the sum of our squares equals 2. Okay, this is our SS, our sum of squares. Easy. And the sum of squares is one of the most important quantities in all of statistics. It's going to be used in all sorts of different statistics. And that's all it is. It's just the sum of the squared deviations, and we squared them just to get rid of the negatives so that it didn't mess up our math. Okay. And then you're going to take the average of that. We want to know what the average deviation is. So you're going to take the sum of squares and divide it by the total values. You're just going to do a mean formula, okay? It's simple, piece of cake. You're not doing anything crazy here. So you've got 1 plus 1 equals 2, okay? Divided by how many values there are, which is 2. And that's going to equal 1, which doesn't surprise us that that's the average deviation when the deviations in this case are plus 1 and minus 1. The average deviation is 1, okay? So, so this gives you the variance, okay? The variance is the term that we call the average, in this case squared, because you can't take average unsquared, so the average squared distribution. Super easy, okay? So to get the variance, the average squared distribution, you take the standard, you take the sum of squares and you divide it by the number of values. Just like to find the average of a bunch of numbers, you're going to take the sum of the values and divide by the total number of values. Okay, it's no different. So you're taking either the sum of values for the typical average, or you're taking the sum of the squared values for the average squared distribution. Okay. So this is basically the same exact formula. You're getting those values in a little different way in order to figure out what's the average deviation. But again, you can't get the average deviation without squaring the deviations because of the issue with the negatives. Okay. And then, of course, you want to get rid of that squared, because if we take our simple example, okay, then this might be points, okay? People are either one point above, or 1 point below on a test, okay? So now we have, since we squared it, we now have squared points, okay? So this right here is 1 point squared. Oops. 1 point squared, which makes no sense to have a squared point or to have a squared degree or something like that. And so then you take the square root to undo the squaring and get back to the original unit. Now, if you take 1 and you take the square root of 1, it's still going to be 1. Okay, so it doesn't change anything in this example. But we're going to go through our temperatures for the spaceship so that you can see for yourself how this works. But once you take the square root, now we get what we call the standard deviation, which is the most commonly used measure of spread. Okay, so let me walk you through this again with our launch temperatures. Okay, so the computation step by step. Let me put up at the top mu, or the mean, right? Just for our reference, is 69.57 degrees. So for each of the 23 temperatures, you're going to need to subtract the mean, square the result, and add them up. Okay, so the mean isn't a round number, so the deviations are messy. That's normal. Real data is messy. But I want you to pause, and I want you to go through and do every single one of these. I know 23 is kind of a lot, but it's going to be really good practice, and it's simple. Just use your calculator, pause it, and do this. So you're going to take the value, you're going to subtract the mean, you're going to get whatever value, okay, and then you're going to square it. Okay, so let's do that real quick. If you, hopefully you've already done this. If not, pause it, but we're going to go through it. So we're just going to do a few for this example. Okay, so if you have 53 degrees, okay, 53 is the value, minus the average of 69.57. We've already done this one, but that's negative 16.57. If you square it, you get 274.57. Okay, 57 degrees. 57 is the value minus the mean, 0.57. Try not to mess up like that, like I do. That's a deviation of negative 12.57. We can't have negatives, so we're going to square it. Okay, and the square is 158. Okay, this one's exactly. And try not to be messy like me and write it on 2 lines like that. Here, let me start to the side a little bit more. So 58, oops. My brain always gets ahead of my hand. 58 is the value minus the average of 69.67. That equals negative 6.57. We can't have negatives. And now if we square it to get rid of negatives, we also have to square the positives, so don't forget that. So negative 6.57 squared equals 43.16. Okay, one more, 67 degrees. Okay, minus 69.67. That gives us the deviation in degrees, which is 6.6. Now that's positive, but we're still going to square it because we're squaring all the negatives, and so that equals 6 times 6.6 equals 43.56. Okay, so you're just going to go through the whole list and do each of those calculations. Okay, if you add up, I know I did a little messy, but the unsquared deviations, okay, before you square them, those will all add up to 0, which confirms that your mean and your calculation is correct. Okay, so then once you square them, you're going to add up all the squared deviations. Okay, so you're going to do the sum of squares, and sum is written like that. That just means sum. So the sum of the squares, or as we write it, SS. Okay, that's usually how we write sum of squares. So all of these calculated up, all 23 of them calculated up, will equal the sum of squares. Okay, that's easy. You're just adding up all the squared values. That's all the sum of squares is. Okay, so the sum of squares, I'll do the math for you, or hopefully you've already done it, is 1095.65. That's what the sum of all the squared values are. Now you're going to divide by n, okay, to get the average, the total number of values. However, here's a little trick, okay? We're actually going to divide by n minus 1 because this isn't every spaceship launch that's ever been done. This isn't the entire population. This is just a sample. So our launch temperatures are not every possible launch temperature ever that could ever be done or ever have been done, okay? They're a sample taken from a much larger set of potential launch conditions, okay? So because it's a sample, it's a little bit less than the total, right? The sample is less than the total population. So we have n minus 1, okay? And this correction is called Bessel's correction, and it exists because samples tend to underestimate variability. So what we found is that dividing by n minus 1 slightly increases the variance and gives us a more accurate estimate of the true population. So just remember, this is not the whole population. If it was the whole population, we would divide by n like we do with the typical average. But because we are finding the average of a sample, a sample's a little bit smaller than the population, so the n has to be a little bit smaller too. That's n minus 1. Hopefully that's a trick to help you remember this, okay? So when you have the entire population, you use n. When you're estimating from a sample, you use n minus 1. And in real-world data analysis, especially engineering and safety data and everything, it's almost always n minus 1. So you're just going to assume that it's n minus 1. Okay, so you take the sum of squares, which equals 1095.65, divided by n minus 1, and that gives you the variance, okay? Equals the variance, which is, so remember n is 23 minus 1, Bessel's correction, okay, because it's a sample. And so now the variance is 49.80. Okay. So, and this formula right here, this number right here, that is the variance. Okay. And the variance is the average squared deviation. Variance equals the average of the squared deviations. Average squared deviation. So variance is just a fancy word. You took all of the deviations, you squared them to get rid of the negative, then you took the average of that, and because it's a sample, we kind of fudge that bottom number, the denominator, so we subtract 1 from it because sample is smaller than population, and then we get the average of all of those squared deviations, which instead of saying average squared deviation because it's a mouthful, we just say variance. Okay, hopefully that's very simple for you. Okay. So now the problem is the variance, or the average squared deviation, is, what is that again, 49.8 degrees. Okay. Except it's not 49.8 degrees because you squared everything, and when you square something, you also have to square the measurement. So now we have 49.8, I'm not even sure how we write this, squared, no, let's see, I think maybe we'd write this like this, squared degrees. And what is a squared degree Fahrenheit? Okay, it doesn't mean anything. There's no such thing as a squared degree Fahrenheit. Okay, that's a fictional measurement. It doesn't exist. Okay, so it doesn't mean anything you can picture. It's not something that you use, but it's simply there because we squared all the deviations. So now to get it back to something that's interpretable, that a unit that actually makes sense, we then have to take the square root of this, so that the degree, it loses that square. Now it's just a degree instead of a degree squared. Okay, so the square root of 49.8 is, pull out your calculator and do this, pause it, and do this on your own, 7.06. Okay. And let me just fix that. 7.06 degrees instead of degrees squared. Square degrees Fahrenheit aren't anything. So what does this mean in plain English? So it means that temperatures in this data set for the spaceship typically deviate from the mean by about 7 degrees. The vast majority of temperatures are 7 degrees above or 7 degrees below, which is very close to the interquartile range that was 8 degrees. Okay, so even though this is a better calculation of variation, it was close to the interquartile range. Okay? The interquartile range did a good job. So most launches happened roughly between 62 to 77 degrees. So 1 standard deviation on each side of the mean. So the standard deviation is the most commonly used measure of variability. It's your ruler for measuring how unusual something is. Hey, Mom.
Hey, kiddo.
How you doing?
So I'm doing fine. How are you doing on this day of growing older?
Old. No, I'm doing fine. I'm just recording how to calculate standard deviation.
Oh, what a fun thing to do on your birthday.
Yeah, it's lovely. I'm sure my students appreciate me spending my birthday this way too.
They do.
Yep.
I'm sure of it. Oh, how nice.
Yeah.
Well, happy birthday.
Thank you. So, what does this mean in plain English? It means temperatures typically deviate from the mean by about 7 degrees. Most launches happened roughly between 62 to 77, 1 standard deviation on each side of the mean. So the standard deviation is the most commonly used measure of variability. It's your ruler for measuring how unusual something is. If it's in the first standard deviation, it's normal. Second standard deviation, a little bit abnormal. Third standard deviation, kind of getting weird. Fourth standard deviation, super, super unusual, super, super rare. 5th, 6th, 7th, those almost impossible. Okay. So now that you've seen the formulas in action, let me introduce the notation that you'll encounter in your textbook, especially because I was actually using some wrong notation when I was talking about stuff. It's still all the same meaning and everything, but let's get more precise about this. When statisticians talk about the population, the entire group of interest, this is when you should use the Greek word mu, okay, for the mean. So this is population level. I was using it for sample, so I was actually using wrong thing. Professors aren't perfect either. Okay, so mu, which means mean. Okay, that's the population mean. The word, the letter for the population mean. Okay, when you're talking about a sample, to show the mean, you just write m or x bar. Okay, that's the sample mean. For the standard deviation, you do sigma, so either sigma squared or just plain sigma. So this is obviously the squared standard deviation, and this is the regular standard deviation for the entire population. If you're doing it for a sample, then it's just S squared or S for the standard deviation. Okay, so our 23 launches are a sample. It's not every launch that has ever happened, that could ever happen. It's just the ones that did. So our numbers are sample statistics. So for sample, the mean, the sample mean, or X bar, okay, is 69.57. Okay, the squared standard deviation is 49.8. Okay, and then the standard deviation, this is also variance, remember the term? Okay, the average squared deviation. And then once we take the square root of that, okay, then we get the standard deviation, so which was 7.06. Okay, so that's important. Obviously, even I still make mistakes, so try to memorize that it is different. So we actually use, this is the Roman alphabet for sample, and we use the Greek alphabet for population. And one way to remember that is if you know your history, the Greeks came first, and then the Romans were sort of their descendants, not genetically, but like socially, culturally. The Romans took on the Greeks' culture and then spread it out to the world, and everything sort of came from there. Hopefully you know the history of Western civilization, because that's pretty basic stuff. But the Greeks started first. The Greeks were the beginning. The Greeks were the really important ones. So we use them for the population letters, and then the Romans for the sample, because the Romans sampled from the Greeks. Okay, if you know your history, that makes sense to you. Okay, so think of it like, tasting a spoonful of soup to judge the whole pot. The spoonful is the sample, the Roman letters, the pot is the population, the Greek letters. Okay, pot, population, Greek letters. So, yeah. So what does the standard deviation tell us? Okay, so if we look at a bell curve, okay, that is not a great bell curve, but let's just pretend it's very normally distributed. So the standard deviation isn't just a number. It's a ruler for how unusual any value is. Remember, our standard deviation was 7.06? Yeah, 7.06. Okay, so we'll just keep that in mind. So if we look at a normal distribution, actually, let me try to draw it a little bit better. I'm not good at drawing. There's a reason I went into psychology and not art. I'm divide it by the middle, and then maybe I'll do a little bit better job. No, okay. Anyhow, we did the best job we could. So if we look at how a normal distribution works, okay, the standard deviation divides the data into predictable chunks. Okay, so start with the simplest fact. The bell curve is symmetrical, right? Or it should be. It should be the same on each side. 50% of the values are above. Okay, 50% is up here. 50% is down here. Okay, unless I draw it. Now add more details. If you look at the standard deviation, okay, so this is the first standard deviation. Somewhere around 34% of values fall between the mean and the standard deviation. 34% above, okay, this is the first standard deviation. So if you looked, this is a 1S, just in case that's confusing. So if you look at like the IQ, the standard deviation is 15 points. So it would be 15 34% of people are 15 points above, and 34% are 15 points below the mean. For our standard deviation, most launches, 34% of launches were 7 degrees above the average temperature. 34% are below the standard. 34% are 7 degrees below the average temperature. Okay, so almost everything, 70% of everything falls within one standard deviation. Okay. Now, the second standard deviation, so another 7 degrees for the spaceship, another 15 points for IQ. So we have the second standard deviation. And then also on this side, the second standard deviation. So now it's getting unusual. Not crazy unusual, but if you fall into the second standard deviation, yeah, it's a little unusual. About 14% of people are up here, and 14% of people are down there. So 28% of people are in the second standard deviation. Okay, that's almost everybody in the entire population is now within just 2 standard deviations. So you have roughly 70% plus another 28%. Okay, so nearly 100%. We're somewhere around like 97% or something like that. Okay, fall within 1 and 2 standard deviations from the average. So almost everybody. If you meet somebody, you know, if this is the IQ test, then the average is the average is 100 points. The standard deviation is 15. So 70% of people will be within, let's see, what is that? 85 points to 115 points. So almost everybody you meet, 7 out of 10 people you meet are going to have an IQ in that range. Another 15 points, you've got 70 to 85, and then 115 to 130. So somewhere around like 97% of people you meet are going to be within 70 to 130 in IQ range. So you meet somebody, it's a good guess that they're going to be there. Now they may not be. You'd have another 15 points above to 145, 160. Einstein was 163. So now we're talking, see, that's 2 standard deviations, 3, 4. He was in the 5th standard deviation. That's almost non-existent. Okay, only 2% of people are in the 3rd standard deviation to either side. Okay, the 3rd standard deviation. And then if you get into the 4th standard deviation, it's like 0.001% or something really crazy low like that. Okay, so it's pretty amazing. So yeah, so 50% to either side, and then 34%, and then 14% in the next one, and then 2% in the next one down. Okay, that lets you make a quick estimate without calculators if you sort of memorize the blocks, the standard deviation blocks. Okay, now there's a rule that also helps if you combine these blocks. Okay, so 34 and 34 is 68%, right? And then 34 plus 14 is now 95. I think I said 97, but it's 95% of the population. And then you combine the 2 plus 14 plus 34 plus 34 plus 14 plus 2. Now you have 99.7% of everybody. So it's the 68, 95, 99.7% rule. Okay. It's also called the empirical rule. So this just gives you a really quick ability to guess. Okay, let me just do it one more time. Within 1 standard deviation, actually it was more likely we see it in SD, okay, is 68% of people. Okay, so again, if we look at the curve, okay, first standard deviation, 34 and 34 together is 68. If you add in the second standard deviation, it's going to be 14 and 14. Okay, so that's 28% plus the 68%. Now, everybody in this total zone is 95% of the population. Then you add in the third standard deviation, which only 2% of people fall in. Now you get within the entire 3 deviations above and below, you get 99.7% of the entire population is going to fall within there. So you can see if you're in the 4th, 5th, 6th standard deviation up, you know, you're getting weirder and weirder, more unusual, more deviant from the average as you go up or down into the further standard deviations. Okay, and this will be important when we get into the probability chapter too. So, all right, so let's test this on our data. Okay, so let's check whether the launch temperatures follow this pattern. So again, the mean, or X bar, of our sample is 69.57, and then our standard deviation is 7.06. So within 1 standard deviation, to calculate that, you're going to have, you know, you've got your normal distribution, you've got the average is 69.57. So if you add 7.06 to that to get to the 2nd standard deviation, 69.57 plus 7.06 is 76.6 degrees. It's the first standard deviation. And then minus, so you've got the average of 69.57 minus 7.06 standard deviation. And then that, if you, 69.57 minus 7.06 is 62.5, okay? So the rule would predict that 68% of people fall with between 62.5 to 76.6. Okay, let me make that a little easier to read. I'll do a different color. Okay, so first standard deviation, you've got 62.5, and then what's the other one? 76.6. Okay, that's the first standard deviation. 68% of people are going to fall in there. Then you add another 14%, another 14% when you get to people in the second standard deviation. So you're going to add another 7.06 degrees to 76.6, and that brings you to, I'll do a different color. That brings you to 83.7, and then on the bottom side, you take 62.5 minus the standard deviation of 7.06, and that's going to equal 55.5. Okay, and the amount of people who fall between 55.5 and 83.7, this should be easy by now, that would be, okay, 95%. Okay, see, sometimes it's difficult even for me to remember. And then the third standard deviation, easy, you just take 55.5 minus 7.06, that's going to be 48.4, 83.7 plus 7.06 is going to be 90.8, okay, we're the third standard deviation. And then that's going to be 99.7% for this entire thing. Okay, that's the empirical rule. So within 3 standard deviations, the rule predicts 99.7% of your sample will fall between there. Okay, so all 23 of our temperature values fall in this range, the 3 standard deviation range. Okay, so the empirical rule works. Our launch temperatures are approximately normally distributed. So now the standard deviation is the ruler, okay, to understand what's normal and what's not normal. Okay. Now, of course, all of our temperatures fall within this range except for the fatal temperature of the day the Challenger exploded. Okay, so the standard deviation is the ruler. The z-score is the measurement you take with that ruler. So let's talk about z-scores. So a z-score tells you how many standard deviations a value is from the mean. Okay, instead of the actual number of what is the standard deviation, how much do people typically deviate from the mean, or how much does your value typically deviate from the mean? This is how many standard deviations a value is from the mean. Okay, and the reason why we like z-scores is because it just standardizes things. It's very easy to understand. So if I say the standard deviation of the IQ test is 15, then you have to know what the average is of the test, and you have to know what the value is, and then you have to calculate it in your head to try to figure out how far from average it is. It just takes a lot of effort. Right? And look at this situation with the Challenger. We needed something to tell the management that was very easy to understand very quickly. It's the middle of the night. Everybody's tired. It's difficult for the brain to work. They're under a lot of stress because there's a lot of pressure to put on this big show for the entire world. All these children are going to be disappointed tomorrow. So the standard deviation, it tells you something. But it's not quick enough. Z-scores are quick. Z-scores, you immediately know how far you are from average. Okay, the Z-score tells you how many standard deviations you are from the mean. Okay, so the formula is pretty straightforward. Okay, so a Z-score, Z equals your value minus the mean, and then divided by 2. Okay, easy. I'm sorry, I did that wrong. Divided by the standard deviation. Okay, so a z-score, and by the way, S, SD, it's all the same. Usually when we're doing equations, we use S, and when we're writing things out in research papers, we use SD. It means the same exact thing. Okay, so let's look at what the z-scores mean before we actually calculate them. So a z-score of 0 means you're exactly at the mean. You're not above it, you're not below it, you're not deviating from the mean. A z-score of +1 means you're 1 standard deviation above. -1 is your 1 standard deviation below. -2 is your 2 standard deviations below. +2 is your 2 standard deviations above. Plus or minus 3, now you know your 3 standard deviations. So it's getting normal, a little unusual, a lot unusual, super unusual, and then 4 standard deviations is crazy unusual. So the farther the z-score is from 0, the more unusual the value is, just like what we were showing with the distribution. Okay, so it means exactly the same thing. So let's compute it. Okay, so again, we know that our mean, or x bar, was, you should have this memorized by now, 69.57 degrees, okay, Fahrenheit. Our standard deviation was 7.06 degrees. So let's convert several temperatures to z-scores, okay? So we'll do one together, and then you should pause it and decide for yourself or calculate for yourself. So the typical launch, 70, an average launch. So your value, okay, we're looking at the formula up here. So z equals x minus the mean divided by the standard deviation. So the value is 70, we're looking at the 70-degree launch, minus the mean, which is 7.06, divided by the standard, So we're looking at the value, which was the 70-degree launch, minus the mean, which is 69.57. Okay, so what's the deviation? How far does our score deviate from the average? And then divide it by the standard deviation, which is 7.06. Okay, and that standardizes it into our z-score. Okay, so this is 0.43 divided by 7.06, which equals plus 0.06. Okay, so a very, very tiny z-score. It's essentially 0. It's right at the mean. This is the most ordinary temperature in the data set. Okay, totally safe to launch. We know that works. That's the average. The warmest launch, let's calculate that. So what's our z-score formula? Pause it and see if you can write it down. Z equals our value minus the mean, because we want to see how far our value deviates from the mean. And then we standardize it by dividing it by the standard deviation. Okay? So we're looking at the warmest launch temperature, which was 81 degrees, minus the mean, which was 7.06. Yes? Okay, good. Oh, sorry. Oh, I keep doing that. Minus the mean, which was 69.57. 0.57, okay, divided by the standard deviation, which was 7.09. Okay, so 81 minus 69.57, the deviation was 11.43 degrees. Divide that by the standard deviation equals, oops, sorry, this is 7.06, equals positive 1.62. Okay, so it's about 1.6 standard deviations above the mean. It's above average, but it's well within the normal range, okay, within 2 standard deviations. So using the 50, 34, 14, 2 rule, about 5 to 6% of values would be this high or higher. Okay, it's warm, but it's not extraordinary. That's not super unusual. Now let's look at the coldest previous launch. Okay, not the coldest ever, the previous one. So write down the formula. Okay, if you're following along, pause it and write down the formula. Z equals your value minus the mean, because we want to know how far it deviates from the mean, and then standardize it by dividing by the standard deviation. Okay, so our value is 53 degrees minus the mean, which is 69.57, okay, divided by the standard deviation, which is 7.06. Okay, so 53 minus 69.57 is negative 16.57. Divide by the standard deviation, 7.06, equals negative 2.35. So a little more than 2 standard deviations below average. Okay, so if you use the 50, 34, 14, 2 rule, only about 1% of values fall this far below. So this launch was unusual. And like I said before, it produced the worst performance data in the program's history. Okay, now that number matters. That number should have gotten their attention already, and it didn't. Okay, so now the temperature of the Challenger when it launched was 36 degrees. So again, take a moment, pause, write out the formula. Z equals the value you're looking at minus the mean, so you can see the deviation, divided by the standard deviation to standardize it. Our value is 36 degrees minus the mean of 69.57, divided by the standard deviation, which is 7.06. So 36 minus 69.57 is negative 33.57, divided by the standard deviation, equals negative 4.76 z-score. Negative 4.76. That is hugely below the average. Almost 5 standard deviations below the average. That should strike you of how unusual this is. So if you look at the 68, 95, 99.7 rule, it says that 99.7% of all values fall within 3 standard deviations of the mean. A value at 4.76 standard deviations is so far out that the normal curve can't even represent it. In a normal distribution, fewer than 1 in a million observations fall this far from the mean. Okay, so if anyone in that teleconference had said this launch temperature is 4.76 standard deviations below the mean of all previous launches, the conversation might have gone very differently. Okay? And of course, you have to understand what the z-score means as well, which is why you're taking statistics. Okay? One of the problems in that conference was that the managers didn't understand the data. They didn't understand what things meant because they probably hadn't taken a statistics class, or they hadn't been taught well. Okay? Or they let AI do their work instead of doing it. Just kidding, they didn't have AI back then, but let that be a lesson to you, okay? So notice what the z-score does that the raw temperature can't. 36 degrees sounds cold, but manageable. So a manager might think, well, it's cold, but it's Florida, whatever, cold snaps happen here. But 4.76 standard deviations below the mean is a statement about a statistical near impossibility. There is no casual response to that number. Like, you can't respond to that casually, like, oh, that's no big deal. That's a huge deal. Okay, and for the next coldest one to be only negative 2.35 of a z-score, and then we're doubling it down to 4.76. Okay, the z-score gives us a vocabulary for extremeness. So you've got somewhat unusual, 0, a z around 1, Quite unusual, Z around 2. Very rare, 0 around 3. And a Z beyond 4 is essentially unprecedented. Okay, so you can see how presenting it as a Z-score, it helps us to immediately know how rare and unusual it is. It's much more powerful in that sense, in the ease of understanding, than the standard deviation or the variance or anything like that. Another thing that we can look at is, the 50, 34, 14, 2 and everything, the empirical rule, it gives us quick estimates, okay? But if we want an exact percentage, we have to use a normal curve table, which is also called the Z table. So the table has 3 columns. It has Z, the Z score. Okay? It has the percentage mean to Z, so the percentage of values between the mean, between the average, and that Z score that you're looking at. So how many values, what percentage of values fall between the mean and your Z-score. And then the percent in the tail, the percentage of values that are beyond the Z-score in the tail. So the table lists only positive Z-scores because the bell curve is symmetrical, so it doesn't matter if it's positive or negative. The tail percentage for Z equals plus 2.35 is exactly the same for Z equals negative 2.35. So for any Z-score, percentage of mean to Z plus percentage in tail always equals 50%. Okay, and this makes sense. Exactly 50% of values fall on each side of the mean. So the area from the mean to Z plus the area beyond Z must add to 50%. So let me draw this out so that you can understand it visually. Okay, so you have the normal distribution. Okay, roughly normal. So you've got 50% above, 50% below the mean, okay? So your Z-score, wherever it falls, let's say it falls right here, okay, maybe somewhere between 1 and 2. The Z table is going to tell you what percentage falls between the average and your Z-score, and it's going to tell you what percentage falls between your Z-score and the end of the tail. Okay, that's what the Z table is giving you. It's very simple. Okay, so if you calculate these two, it will equal 50%. Okay, because only 50%, because you're going to have the same thing on this side. Okay, and so whether the Z-score is positive or negative, it doesn't matter, because it's going to be the same percentage between the tail and the Z-score and between the Z-score and the mean. So that is also going to equal 50%. Okay, hopefully that makes sense. So every time you use the table, follow these steps. Step 1 is convert to a Z-score, get your Z-score. Step 2 is draw the normal curve. Or try to. Okay. Step 3 is make a rough estimate using the 50, 34, 14, 2 rule, okay? And sort of guesstimate what percentage that you're going to fall into. Step 4, look up the Z in the Z table and check that your answer matches your estimate, okay? So drawing the picture isn't optional, it's not a suggestion. Students who skip the picture, making the picture, make errors. So the picture tells you which column to use and whether you need to add or subtract percentages. So let's do an example. So how unusual was the 53-degree launch? So we computed Z equals negative 2.35 for the coldest previous launch. What percentage of launches would be this cold or colder? So step 1 is the Z equals negative 2.35. So draw the curve and then mark negative 2.35. Okay. So you've got a standard deviation of 0, a standard deviation of 1, 2. This would be 3, so negative somewhere around here, 2.35. Okay. And then you want to shade the tail to the left. That's the area that we want. Okay, so everything, so from here over, that's the tail. Okay. So the rough estimate, the tail at Z equals 2 is about 2%, right? It's in that 2% area. So at Z equals 3, it's actually 0.15%. So Z equals 2.35 should be between 0.15% and 2%. So if you look up Z equals 2.35 in the table, ignore the negative sign, okay, because the table is symmetrical. The percent in the tail is 0.94%. Okay, 0.94% is between 0.15 and 2%. That makes sense. So less than 1% of values in a normal distribution fall this far below the mean. Only 0.94% of values fall this far below the mean, this far or lower. Now, if you look at a z-score of 4.7, you probably won't even find that on a typical z-table. They usually barely go to 3, let alone something as extreme as 4.47. That's how unusual it is, or 4.7. You just don't even see that. But the percentage of that, it's less than 1 in a million. That's how unusual that temperature was. So now I can tell you exactly what happened. The Challenger's solid rocket boosters were assembled in segments. Each joint between segments was sealed by 2 rubber O-rings, which are rubber gaskets designed to prevent 5,000 degree combustion gases from escaping. The rubber needed to be flexible. It had to compress when the joint was assembled and then spring back to seal the gap when the booster ignited. The engineers tracked a damage index, measuring how much hot gas got past the O-rings on each flight. Here's the damage data alongside the temperatures that you've been analyzing. At warm temperatures, the rubber was resilient. It compressed, bounced back, sealed, 0 damage. At cold temperatures, it stiffened. It lost its resilience. It couldn't spring back fast enough. Hot gas got through. At 36 degrees, the rubber was essentially rigid. It couldn't seal at all. Hot gas burned right through the joint. It reached the external fuel tank, and the shuttle was destroyed. Physicist Richard Feynman demonstrated this during the investigation. He bought a cheap C-clamp at a hardware store on the way to a televised hearing. He compressed a piece of O-ring with the C-clamp, and he dropped it into a glass of ice water to mimic the temperature of the O-ring at the time. When he released the clamp, the rubber didn't spring back. It just sat there deformed. His words, "I believe that has some significance for our problem." So you just did with statistics what Feynman did with ice water, and each tool you used told you something specific about the danger. The mean told you that the center was 70 degrees, which in a sense proved useless for that question, for the question that mattered, right? At least on its own. But notice that we did use the mean for all sorts of calculations. So the mean's still useful, but on its own, it just doesn't tell the whole story. The range told you that 36 degrees was 17 degrees below anything ever tested. The rubber had never been asked to work at temperatures this cold. The interquartile range fences told you that 36 degrees was 19 degrees below the outlier threshold. So this wasn't just unusual, it was off the chart. The standard deviation told you that temperatures typically varied by about 7 degrees. And 36 degrees was nearly 5 of those units of 7 degrees away from normal. The z-score told you that 36 degrees was that almost 5 units away. It was 4.76 exactly, standard deviations below the mean. A condition that basically is so rare it almost never occurs. So this had not been tested for safety whatsoever. The normal curve table confirmed how extreme this is with exact percentages, less than 1 in a million. So the engineers had this data, but they couldn't make it speak. Okay, they weren't statisticians, and they weren't presenting it in a way that was understandable, like the z-score makes it understandable, like this data that we just went through makes it understandable. The lead O-ring engineer, Roger Boisjoli, later said, "I fought like hell to stop that launch." But when NASA reversed the burden of proof from prove it's safe to prove it's dangerous, the engineers couldn't meet it. Not because the data was ambiguous or confusing or left any doubt, but because they couldn't express what the data showed in the language of statistical precision. You now hopefully have that language. So today we analyzed one data set with 23 different launch temperatures with every tool in the statistician's kit: central tendency, range, interquartile range, standard deviation, and z-score. So when you learn these tools, you're not learning to pass a statistics class. You're learning a language for quantifying uncertainty, for making the invisible visible, for telling the difference between this is unusual and this is unprecedented. And sometimes that language has the ability to save lives. So Feynman closed his part of the Rogers Commission report, this investigation into the shuttle, with a line that belongs on the wall of every statistics classroom. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. In other words, we need to face reality over just how we want things to be. And statistics is one tool for being able to see reality. So, all right. So if you have any questions, just let me know, and I hope you guys learned a lot with this lesson.